Spirit of Maths, the channel devoted to mathematical curiosities. To motivate this video, let's start by a simple remark. If you have a bijection between two finite sets, phi between A and B, then the cardinal of A is equal to the cardinal of B. This means that A and B have the same number of elements, because a bijection is a correspondence between the element of A and the element of B. But when we drop this hypothesis finite and we deal with infinite sets, we can see some strange phenomena. Let's start by sets which are in bijection with the natural number. These sets are known as countable. And here we can see that a subset of natural number, namely the set of even numbers, is actually in bijection with n. So this map which to any even number associate n over 2 is actually a bijection. So here the sets have a priori less number than n, but we can make a correspondence between this set and n. And more generally, any infinite subset x of n is actually countable. We can make a bijection between this set and the natural number. And we can do so by considering this sequence. We consider P0 is the minimum of x, and we consider P1 is minimum of x minus P0, and so on. And we get, it's actually what we do is we order the element of x increasingly. And the bijection is this map with two n associated Pn is actually a bijection. So any subset x in n is actually can be made in correspondence with the natural number. But now, what happens if we have some sets which seems bigger than n? For instance, relative numbers, rational numbers are real numbers. And in today's video, we will build an explicit injection from the rational numbers, q, into the natural numbers. And actually, we will show that q is countable. To do so, we first give a bijection between the set of relative numbers with the natural numbers. It's easy and it's easy to do, and we will use a famous function, namely Cantor's pairing function, which is a map between n squared to n given by this formula, and we will show that actually it is a bijection. And it is the core of this video. We will see that it's not easy to show that this map is a bijection. We will show that it's a bijective, and we compute its reciprocal. And we will use this bijection and pairing and Cantor's pairing function to give explicitly an injection from the rational numbers to natural numbers. And this will permit us to show that rational numbers are countable. So let's go First, the bijection between z and n. It's easy to build. We consider this map from z to n, which associates to any z to z if z is positive. So we get here all the even number of n, and we associate minus 2z minus 1 if z is negative, and we get all the odd numbers. And it's easy to show that it is a bijection, and we can even compute its inverse, the map from n and z, which associates to n over 2 if n is even, and minus n plus 1 over 2 if n is odd. So here we have a bijection between z and n. It's easy. Now we will show that there is a bijection between n square and n, and via the Cantor's pairing function. So we need a lemma. This lemma, it's a crucial lemma in the proof, and this lemma says that for any natural number there exists a unique natural number p, such that p plus 1 over 2 is less or equal to n, and n is less or equal to p1 p plus 2. So this integer is unique, and it's associated to any integer. And actually we will give explicitly the expression of p in function of n. So let's go. First, remark that this double inequality is equivalent to the first one, and the first one is equivalent to p squared plus p minus 2n less or equal to 0, and the second inequality is equivalent to p squared plus 3p plus 2 minus 2n positive. So we need to determine p which satisfies these two inequalities. And first we need to study the sign of x squared plus x minus n. So it's a polynomial expression of degree 2, and to determine the sign of a polynomial expression of degree 2, we need to compute its discriminant and its roots. So let's go. The discriminant is given by 1 square minus 4 minus 2n, and we get 1 plus 8n. And the roots are x1 equal minus 1 plus the root square of 1 plus 8n over 2, and x2. So they are the roots, and we know that a polynomial is positive. It has the sign of x squared when x is at exterior of the roots. So we get that this polynomial is negative, is less or equal to 0 if x is between x1 and x2. So now we will do the same for the second inequation. So we compute the discriminant of this polynomial, and it's the same as the discriminant of the first one, and the roots are y1 and y2 given by these two formulas. And we have that this polynomial is positive if x is in between minus infinity y1 union y2 plus infinity. So now we can give the condition on P to satisfy these two inequality. So we need so this P must be between x1 and x2, or and P is less than y1, or P is bigger than y2. And we remark here that y2 is equal to x2 minus 1, and we have that y1 less than x1 less than y2 less than x2. So these two conditions are satisfied if if P is between y2 and x2. It's bigger than y2 and less than x2, and we get that P satisfy these two inequalities if x2 minus 1 is less than P and P is less or equal to x2. And it is well known that there is one unique integer natural number which satisfy this inequality, namely the floor of x2. So P, it is the floor of x2. So we have shown that there is unique for any natural number, there is unique P which satisfy this two inequality, and P is given by this formula. It's the floor of minus 1 plus the square of 1 plus 8n over 2. So now we can pursue to show that Cantor's spiraling function is a bijection. So I recall the inequality. So first we will show that this spiraling function is actually surjective. So we take a natural number here, and we look for x and y such that fxy is equal to n, and we put P, the solution of the previous lemma. So we put x equal p plus 3 over 2 minus n, and y equal n minus p plus 1, and we will show that first that x and y are natural numbers, and f the xy is equal to n. So first remark that p plus 1 over 2 is a natural number, because 1 of p or p plus 1 is even. So we can divide by 2 and get to a natural number, and from this inequality we have this. So y is a natural number. Now we have also that p plus 3 over 2 equal p plus 1 over 2 plus p. This is a natural number, so p is a natural number, so this quantity is a natural number. So x is also we need to show that x is actually positive. So we have this inequality from this one, because n is less than p plus 1, p plus 2, and if you have two integers a less than b, then a is less or equal to b minus 1. So we have, since here n and this quantity are natural numbers, so we get this inequality here. And we use it to show that x is actually equal to this quantity, and minus n is bigger than minus this quantity. And if you compute this quantity, you get 0, because you have p square minus p square, 3p minus 3p, and here we have 2 over 2 is 1, 1 minus 1 is equal to 0, and we have x is positive. So we have shown that actually x and y are natural numbers. Now we will show that f xy is equal to n. It's easy. We have x plus y equal p from if you from this relation. If you compute x plus y, you get this minus this, you get p. And so if you compute f xy is equal y plus p plus 1 over 2, and we get n. So we have shown that Cantor's function is surjective. And now we will see why we have chosen these two values. Actually, we will show now that Cantor's function is injective, and to do so, we will show that this equation has a unique solution, the solution we have used in the previous proof. So we will show that if we fix n, the solution xy of this equation are indeed given by this formula, where p is the floor of minus 1 plus etc. So let's go. We take xy and we put this equation. First, note that we have that this quantity is less or equal to plus 1, so we have this quantity less or equal to n. Now this is also less or equal to, we can add x plus 1, and we get to strict inequality here. And if you compute this quantity, you get this one. On the other hand, so we have shown that we have this one, n is bigger than 1 and then 1, and what we see that we have here p plus 1 over 2, p plus 1, p plus 2 over 2, and according to the lemma, x plus y is the unique p we have computed later. So necessarily x plus y is equal to p. And so we get that y equal n minus this one, and we can, from this relation, and we compute x is equal p minus, and we have the solution. So the Cantor's function is injective and indeed bijective, and we have computed its inverse. It's given by p plus 3 over 2, n minus p plus 1 over 2, where p is the floor of this quantity. And now we have shown that Cantor's function is actually bijection. And now we can build an injection from the rational numbers and natural numbers. we have a bijection between relative integers and natural numbers. We have a bijection between n square and n, and we will use these two bijections to build this injection. So every rational number can be written in a unique way, p over q, where p is a relative number and q is a natural number non-zero, with this condition that the absolute value of p and q are co-prime. They have no divisor, no common divisor. And we put phi p of q equal f hpq. And now it's easy to show that phi is injective. If we write phi p q equal to phi p prime q prime, we get this relation. Now f is a bijection, so we get hp equal hp prime and q equal q prime, and h is a bijection, and we get that p equal p prime and q equal q prime, and we have down. Now from this injection we can actually build a bijection between rational numbers and natural numbers by using the same trick we have used for subsets of n. So we can write the image of q as an increasing sequence p0, p1, p2, and this map from q to this set is bijective, because phi is injective, and here we take the image, and we can define psi from natural number to rational number by this formula, and we get that there is a bijection between rational numbers and natural numbers, and we have down. Okay, so now to support the channel, please like, subscribe and share, and thank you.